Greetings, this is Mr. T's commentary over intermolecular forces, part 2. We're going to be talking about solution concentration in part 2. We'll be memorizing and applying various formulas to do various types of solution concentrations. As a refresher, a solution is a homogeneous mixture of two or more substances, such as salt and water. Now, the lesser substance that's present is the solute, such as salt in this instance, and the greater amount is the solvent. And of course, the solute needs to be completely homogeneous. That means completely spread out and uniform through the solution. We need to figure out the amount of solute that's going to be present. So we're going to perform three types of calculations using these three formula names. Percent by mass, also known as mass volume or mass percent, percent by volume, and mass volume percent. We summarize it as percent mm, percent VV, and percent MV. So the first M for percent by mass is going to be the grams of solute. And then the second M is going to be the grams of solution. As a reminder, solution is the sum of solute and solvent added together. Now the first one is all about mass, the second one is all about volume, and the third one is a combination of mass and volume. You are going to get a paragraph that looks very similar to this, and then you'll have to memorize the appropriate formula in order to solve it. Please keep in mind that you'll get multiple types of paragraphs, and each paragraph may represent a different formula that you have to apply. So make sure you constantly practice so you can master these, so you don't use the wrong formula by accident. So the first one is percent by mass. It's mass of your solute in grams divided by mass of solution. Here is the paragraph that I could give you. The smaller amount is the solute, so that goes on top. And then you have to solve for the solution. Again, the solution is the sum of the solute and the solvent added together. So there's the grams of solute, grams of solution times 100, and then we just summarize it as percent mm. Now technically the g's cross cancel, but we need to let people know that this is percent by mass, and it is implied that everything was done in grams, so we tend to use percent mm. Although it is possible to use percent g over g, I've seen that before. And then we write the name of the solute. So let's do another calculation just like it. Or we're going to do all three. Alright, so I just did it for you right now. Let me go ahead and change pins so I can make a marker. Let me redo this again. There we go. So I have 7.6 grams. That's going to be the solute. And then I added together the solute and solvent. By the way, it's implied that on top is grams. These two added together is grams. Yes, we have to worry about sig figs. So 2 sig figs on top. And then when we add this together, there's going to be, let's see, almost forgot, 7.6 plus 87.3. It's going to be 1 decimal place, so 94.9 grams. So at least decimal places, when we add them together, And then when you divide, it's going to be least sig figs. So there's going to be 2 sig figs on top, 3 sig figs on bottom. So the final answer is rounded to 2 sig figs. The next one's a little bit trickier. You'll notice we have grams here, but then we have mils. So we have to let you know that we're looking for percent by mass, or mass percent, and notice that M. So we have to make a grand assumption that density of water is 1. So doing a conversion factor, we can automatically assume that 1 mil is equal to 1 grams. Ergo, the mils is actually going to be equal to grams. So to come up with the grams of solution, it's going to be 500 grams of water plus 24.0 grams of our solute, and then that sum is going to be 524 grams of solution. So you then go ahead and do a division times 100, and then here is our mass percent. And you'll notice I interchange the term mass percent by mass. I could use either term. The next one is pretty much the same problem, only I did it out of 1500 mils instead of 500. And again, the top is going to be solute of grams, bottom is going to be solvent of grams. We assume that that 1500 mils is turned into 1500 grams, and then you add it to the solute, giving you 1524 grams of solution. Here's the final answer. So make sure you practice and practice these types of calculations. Let's move on. We're now going to get into percent by volume. Now, in the past, we went ahead and we simply added together our masses. So if we go back one slide, I added together the solute and the solvent. Unfortunately, when it comes to volume, volume is not additive. You cannot add it together. Experimentally, it won't work. Let me prove it to you. Here I have a flask that contains 50 mils of water and another flask that contains 50 mils of ethanol. When you try to add it together, you'll notice that it falls right below the 100 mil mark. It is not equal to 100 mils. It's something like 96 mils or 97 mils. Pretty cool, huh? Why is this? Well, let's say you have substance A and the structure looks like this, and then you have substance B and the structure looks like this. Notice how one substance is bigger than the other? Well, what will happen is the smaller substance will go ahead and fit into all the little nooks and small spaces. And when it does that, it actually takes up less room when you add them together. So bottom line is volume is not additive. What do we got to do? Then we got to do the experiment. So having memorized this equation, on the next slide I'll give you a paragraph that looks like this. And then I have to experimentally give you the volume of solution. We have to figure out how much it is when we add up together the solute and solvent together. So there it is. Now I'm going to try to trick you sometimes. I could give you the solute, and then I could give you the solvent, and then I'll give you the solution. And then you automatically have to know that for percent by volume, the solvent is not relevant for the calculation because we can't use it. You can only use the solute and the solution. Ooh, I'm so tricky. Yeah, I get that. So let's go ahead and practice really quick. So the top one has been done for you as well as the bottom one. I also put in the units. Super simple calculation. Plug in the solute and the solution times 100, and that gives you percent by volume. So the top one, 25 divided by 100 times 100 equals 25.0% by volume of ethanol. And then the bottom one, another problem, 6 mils, that's the solute, divided by 50 mils, that's the solution, times 100, that equals 12%. Alright, so let's move on. This next one is a combination of volume and mass. Or let me say that another way. Mass of solute divided by volume of solution. Now, because we're dealing with volume of solution and we learned it's not additive, then I have to provide it for you. So in this case, I provided it for you. The calculation is very simple. The only difference is we're going to go ahead and use grams and mils. But calculation-wise, it doesn't get any easier than this. Here are the complete answers. Make sure to write %m over v since it's a combination of mass over volume. Also, there's no changes to the units needed. It's always going to be grams divided by mils. The bottom one's a little bit trickier because your calculator may lie to you when it comes to sig figs, so there should be 3 sig figs. So it'd be 3.00%. Now, the previous ones tend to be used in the health field, such as % by volume or % by mass. Molarity tends to be used in science, such as chemistry. And we love putting all of our concentration units in molarity. Now, molarity, our definition of it is it's going to be moles divided by liters. Here are the worked out problems. Let's start with the first one. We're solving for molarity. The big difference is we're not starting with moles, we're starting with grams. So we need to convert grams into moles using molar mass as a conversion factor, which you've done before. You have to look up the molar mass using your periodic table. And depending on which periodic table you use, it might be a little bit different. Once we have our moles of our solute, we then need to go ahead and divide it by the liters. Now here's another curve. Notice I give you mils. So it's implied that you're going to have to convert mils into liters. So 1 liter is divided by 1,000 mils, and then that gives you 8.00 liters. You then divide moles divided by liters, and then here is the molarity. Yes, you have to worry about sig figs. Starting value has 4 sig figs. Molar mass I used had 4 sig figs, so 4 sig figs divided by 4 sig figs, so it's 4 sig figs. The next one is another molarity problem. It's worded a little bit differently, calculate the molarity, but you automatically have to know, oh yes, I have to use the molarity formula to figure this out. So it's moles over liters. There's the moles, there's the liters, here's the final answer, rounded to 3 sig figs. And then the last one, instead of starting off with the moles, we start off with grams, so you got to do the exact same thing, convert it from grams to moles, and then divide by liters, and then there is your molarity. So you need to be very comfortable with this, especially if you plan to do any more science, because we love using molarity. Now we're going to use molarity as a conversion factor. So at the beginning of the class, we talked about density as a conversion factor. So density was mass over volume. And then I'd give you a problem where I'd say, given 3.0 mils, how many grams is it? And I could have given you a density of 2.0 grams per mil. And you had to turn density into a conversion factor. So 1 mil is equal to 2.0 grams, and then we'd go ahead and we'd use density as a conversion factor, where mils would go on bottom, grams would go on top because it cross cancels, and then we'd solve for our final answer, which would be 6 grams. We're using molarity as a conversion factor. So here are the steps. You need to master the steps. So the first thing we do is we turn the M for molarity into 22.5 1.0 moles over liters of solution, since that's the definition of molarity. And the bottom number is equal to 1. Furthermore, we have to worry about sig figs, so if the top one has 3 sig figs and the bottom one is implied to be 1.00. Here is the equality. Again, it's implied to be 1.00 for liters. And then we can use it as a conversion factor. So let me take you through this. The very first thing we need to do is turn this into a conversion factor. So 0.50 molarity, that's going to be equal to 0.50 moles over 1.0 liters. The top had 2 sig figs, so the bottom should have 2 sig figs. That's why it's 1.0. And then I bring to the side the bottom denominator, liters, and then here is my equality. 1.0 liters is equal to 0.50 moles. In this case, moles of NaCl. Now, I need to go ahead and do the rest. So my starting value has 2.0 moles of NaCl. What goes on bottom? 0.50 moles of our NaCl, and then 1.0 liters of our solution on top. Notice how the moles cross cancels out. And then using the calculator, you should have a final answer of 4.4 liters of solution. So we do the exact same thing for the next problem. Oops, 0.30 liters. Turn it into a equality and conversion factor, which we already did. So then it's going to be 0.50 moles of NaCl on top, 1.0 liters of solution on bottom, and then that gives us 0.15 moles of NaCl. So density, molarity as a conversion factor allows us to convert from a starting liters to moles or a starting moles to liters. So here's the complete setup, and let's go through everything from the top. So we have to go from grams to moles, because notice we're starting in grams. So you have to calculate the molar mass for NaCl, and again, depending on what periodic table you have, you may have a different answer than me. And then once you're in moles of NaCl, you use the molarity as a conversion factor. Moles goes on bottom because it cross cancels, leaving liters of our solution. Now you could choose to put 0.51 liters, or you could say 0.51 liters of NaCl solution. And you could write that here if you wanted to as well, so everything properly cross cancels, leaving the desired words that you would like. It's up to you. Let's do the next one. The wording's a little bit differently, and we've made it a little bit more complicated. So now we want to go ahead and go from mils to grams. So to do this, we need to convert milliliters into liters. So there's that favorite equality we love using. 1 liter is equal to 1,000 mils. Mils cancels out, leaving liters. The molarity is turned into a conversion factor of moles over liter. Liters are on bottom because it cross cancels, leaving our desired moles. Now we need to go one step further because they want to know grams. Ooh, That's rough. So again, you have to calculate the molar mass of potassium dichromate, excuse me. And then there's your grams. Technically, I could have gone one step further and asked for milligrams, but that would just be mean. So sig figs are important. So the first one, 2 sig figs, 4 sig figs, 2 sig figs, because molarities, sig figs are counted. So the final answer is 2 sig figs. This one is 4 infinite sig figs because of the same system. 3 sig figs, 3 sig figs. So it should be rounded to 3 sig figs. That's the least amount. Bottom one is similar to the middle one. Mils to liters, molarity is a conversion factor, and the moles to grams. So practice, practice, practice. You want to master these, as you'll see these on future ones, or future quizzes and exams. Now we can go and once we know how to use liters of solution and molarity as a conversion factor to form moles, we can go ahead and use the balance equation to go moles of one substance to moles of another. So in this case, we started with liters and molarity of HCl. So excuse me, that's confusing. Let me say that again. We started with our starting value of liters and molarity of HCl. We can then use molarity as a conversion factor to figure out the moles of our known. In this case, the moles of our known is going to be moles of HCl. So this is our plan of attack. We form the moles of known. We then use the balanced equation to figure out the moles of the unknown, and then we can figure out whatever step we want after that. We can convert it to grams, we can keep it as moles, we can convert from moles to molecules. So let's go ahead and see these problems in action. I have the setup already created in the outline examples. So if you go to the front of the slides, you'll see the outline and examples. So here's the outline. Under the outline, we have sample calculations for molarity as a conversion factor. Although that word calculations is a bit redundant. Alright, so given a balanced equation, as you see here, how many moles of zinc sulfide are required with a starting 3 liters of 3.0 molarity HCl? In short, I just simply copied the questions you see on slide 13, and then I worked out the problems. So, first off, here is the liters of solution and molarity, like we learned before. You need to go ahead and convert it into an equality for use as a conversion factor. Once we do that, we're now going to be in moles of HCl, and we then go ahead and convert from HCl to zinc using a mole ratio that we get from the coefficients from the balanced equation. And we see up here where the 1 is implied and then the 2 moles of HCl are present right there. This gives you the final moles of zinc. Now, starting value has 2 sig figs. I'm going to use a purple pen for this one. Starting value has 2 sig figs. Molarity as a conversion factor has 2 sig figs. Ratio, it's non-measured, so we ignore it. So the final answer should have 2 sig figs. Let's scroll down here. How many moles of zinc chloride are produced with a starting 5.20 mils of 3 molar HCl? Again, with the balanced equation and the molarity, we go through the same steps. We convert the molarity into an equality for use as a conversion factor. Our starting value is in mils. Now it's not in liters, so in order to find the moles through the molarity, we have to convert the mils of solution that I'm circling there into liters. So we have to do another conversion. Once it's in liters, convert it into moles using the molarity as a conversion factor, then use the mole ratio from the balanced equation. And that gives you the moles of zinc chloride. Now you already learned that when you're in moles, you can then go to moles of grams or moles of molecule. So in the next problem, we want to go ahead and convert to grams of hydrogen gas. So I start off with the liters and molarity for HCl. Again, form the equality. And then we have our starting solution, happens to be in liters, so we don't have to convert that. We then use the molarity as a conversion factor to convert to moles. Then use the mole ratio from the balanced equation. Once we're in moles, we have to go ahead and get the molar mass. So, oops, excuse me. My bad. Let me go ahead and adjust it again. Pen's going all over the place. Alright, let's try it again. Here's the molar mass. 1 mole of H2 is equal to 2.02 grams of H2. We then convert from moles to grams, and then there is our grams. Notice how everything cross-cancels. So the liters cross-cancel, the moles cross-cancel, the mole ratio cross-cancels, leaving moles of H2, and then the moles of H2 cancels, leaving grams. We account for sig figs. So here we have 5 sig figs, 3 sig figs, infinity because it's not measured, 3 sig figs, so it's rounded to 3 sig figs. Let's do the next one. How many grams of zinc chloride are produced with a starting 10.20 liters of 1.2 molarity HCl? So first we're in liters, it's not in mils, so we don't have to do any additional conversion. And then from there, we need to set up our equality from our molarity so we can use it as a conversion factor. And now we're going to go from liters to moles. We have our mole ratio from the balanced equation. And now that we're in moles, we have to go from moles to grams using our molar mass. Now on a quiz or exam, I could give it to you, or you may have to calculate it from the periodic table. And then here is our final answer. So it could be 8.3 times 10 to the 2 if we use scientific notation, or 830 grams zinc chloride, where 0 is a placeholder 0, since there's only 2 sig figs. Why is it 2 sig figs? Well, let's go through the process. 4 sig figs starting value, 2 sig figs in the molarity, and then 4 sig figs in the molar mass. Non-measured is it's infinity for the whole ratio, so the lowest one is 2, ergo 2 sig figs. Alright, so be sure to practice this and of course master it, so you can go through the process as soon as you see the question. Make sure you're able to read the question so that way you can apply all of these steps as needed to get to your final answer. So now we're going to move on to dilution calculations. So I started filling in the setup for these calculations, for the dilution calculation. But first let's go ahead and get into the theory. So let me go ahead and set my pen. A dilution is when we go ahead and we add solvent to a solution in order to lower its concentration. So we make it from concentrated to diluted. So for example, if I had a concentration of 8 molarity, I could dilute it in order to make it 2 molarity, where 8 molar is more concentrated, 2 molar is more dilute. Oftentimes we'll have a bottle that you'll do experiments with, and we call it the stock solution. That's the most concentrated form because it's easiest to store. Saves up a lot of space if we just have a lot of small bottles with concentrated amounts. We'll say that's 8 molarity. And then when you're actually inside the lab, we go ahead and we transfer some of it and dilute it, so that way the bottles during the lab itself may be around 2 molarity. It's less concentrated, so it's less harmful, and we can create a lot more for everybody to go ahead and use. Now let's see this process in detail. The first volumetric glassware, that's our initial concentrated amount. So we call that C1. The initial concentrated amount is also known as the stock solution. Now, our goal is to go ahead and create a diluted amount. We'll call that C2. So if you take a look where it says step 1, we have our initial concentration, our stock concentration of C1, and our goal is to create the diluted concentration, C2, which is what we will distribute to students inside the lab. But we need to make sure that we have the diluted concentration measured out properly. So here is an empty volumetric glassware. And what we're going to do is we're going to use a special transfer glassware called a volumetric pipette. And it's used to suck up some of the original concentrated amount so we don't waste it all. And we're going to go ahead and we're going to transfer it into the empty glassware. So this is step 1. And then here's what it looks like. Oops, take that back. Here is what it looks like afterwards. So there's before, there's after. And we're transferring the liquid into this empty glassware. Now it's slightly filled. So that's step 1. So let's make sure we label everything. So that's our, we have our initial concentration. We then have the initial volume, what we call V1, which is going to be transferred over and placed inside. Now, as soon as we have it transferred over, we're going to dilute it usually with water. That's going to be our main solvent that we like to dilute it to. And we usually have some sort of special glassware which has a mark on there, so that way we can dilute it to that special volume so we know exactly how much is in there. So we're going to go ahead and put in water, and we're going to fill it all the way to the top. So it's filled up all the way to the top where that line is. So this is now the diluted volume. So now we have our diluted concentration and our diluted volume. That's what the extra water put in, and it's the total solution amount. So in summary, we had C1 for our initial stock solution. We had V1. This was the amount that we're going to transfer over to the second glassware. We have V2. That's the total diluted amount from water. And then we have our final diluted concentration of whatever that might be. In summary, it's C1, V1, C2, V2. Looks very similar to Boyle's law, gas law equation. And we use this to go ahead and figure out the amount that we're going to transfer and our final concentration. let's go back to the other slides. How will I test you on this? Well, I'm going to give you a problem that looks like this. So this is a dilution calculation problem. And the minute you see this, you will have this memorized. This is the dilution formula problem, or dilution formula. And you're going to have to plug and chug the values just like you did the Boyle's law. So it's pretty straightforward. So let's walk you through this. So the initial or stock concentration we call C1. Initial volume transferred is V1. The final diluted concentration is C2. And the diluted volume, when we added in the water to that mark on the volumetric glassware, that's V2. So I go ahead and I label everything. And I didn't do it on this one like I did on slide 15. But so I'll label everything. So 2 mils of our 1.0 molarity HCl. So that's going to be V1. That's C1. And is diluted to 20 mils, excuse me. Can't count. 20 mils, that's V2. So what is my diluted concentration? That's going to be C2. So I'll go ahead and I'll put in the values. So there's my volume, V1, C1, and then here is my diluted volume, V2, and my diluted concentration that I want to solve for is C2. Now this is our unknown variable. So we'll do 2 times 1 divided by 20, and then that gives me my final diluted concentration of 0.1 molarity. All of these are measured values, so this is the smallest, let's see, which one's the smallest one? Let's see, they're all going to be, well, 2 of them are going to be 2 sig figs, the other one's going to be 3 sig figs, so it should be rounded to 2 sig figs. The final answer should actually be 0.10 molarity. So I need to add in one more 0 in there. Now you'll notice it didn't match up. I actually reversed it where it says V1 C1 as opposed to C1 V1. That's okay. As long as you have the initial concentration of volume on one side and diluted concentration of volume on the other. It doesn't matter whether you have it to the left or to the right. Let's go ahead and do the next one. I go ahead and I label everything first. So in this case, V1, C1, diluted concentration C2, this is V2. I plug in the values, I solve for my unknown variable, and then here is my final molarity with proper sig figs. And it should be the 2 sig figs. So here are other problems just like it. So I labeled what each component is. I put them into the dilution formula, and then I solve for my unknown. In this case, it's 8 mils of HCl. And it's to 8 because there's only 1 sig fig. The next one's going to be a little bit harder because you'll notice a difference. There's liters and there's mils, and they should be the same unit. Either both mils or both liters. So in this case, I'm going to change mils into liters, and you should already be familiar with that conversion. So it's now 0.0900 liters. I then go ahead and plug in my values and then rearrange to solve for my unknown concentration. So the lowest amount is 2 sig figs, so it should be rounded to 2 sig figs. And I do the same pathway for the next problem. Convert mils into liters, label everything C2, V2, C1, V1, place them into the dilution formula, solve for my unknown, rearrange it, solve for my unknown, and then there is my final, in this case, molarity, diluted concentration. So make sure you practice with these problems. Alright. Now we finished with the math. Now the rest is just going to be concepts, or there's actually one more easy math problem to do, but you'll like it. So this topic is on particle size. So in a solution you have solute and solvent components. Well, we just focus on solute and the size. So we have the smallest particles, what we call true solution particles. We have medium-sized particles called colloids, and then we have large particles called suspensions. Now I'm not going to have you memorize any numbers for the diameters of each. I won't do that. I do want you to be familiar with the different properties and the three different types. Here's the first two, true solution and colloids. True solutions are the smallest solute particles. The smaller the solute particles, the more likely it's to spread out evenly and form a homogeneous mixture. And homogeneous mixtures, another term for that in chemistry, is true solutions, as opposed to heterogeneous solutions where they're not mixed up properly. The bigger the particle size, the less homogeneous it tends to be, because the particles tend to clump up to each other. So smallest particle size, completely homogeneous for true solution, and they can pass through some semi-permeable membranes. Now there are special barriers called semi-permeable membranes, and they have tiny little holes in them. And they allow some solute particles to go through, such as ions of sodium and chloride, but other particles they don't allow. So for example, if you were to have a giant particle, such as a good example would be a giant protein, for example. Protein that you might find in your blood, for example, like an immunoglobulin. And obviously that size, it's too big to get in. Now true solution particles, they're small enough that they can pass through most semi-permeable membranes, allowing the solute particles and water molecules, and other small particles the size of water, to pass through. And then other large particles they can't pass through. Now there are different sizes of semi-permeable membranes. Let me go ahead and start that over, please. Now there's different sizes of semi-permeable membranes. There are ones with very small holes, and the holes are so small that they may allow salt ions to go through. But maybe they don't allow bigger molecules such as sugar molecules, which are a little bit bigger. And then we have larger semi-permeable membranes, which have bigger holes in them, which could allow sugar particles to pass through, but they wouldn't allow larger molecules such as protein molecules, which may be really big. So examples of true solution are what I just talked about: salt, sugars, water can pass through, although that tends to be a solvent, not a solute. Colloids are medium-sized particles. So I made a big deal about those special molecules. We even call them macromolecules because they're pretty big, called proteins that are found in your blood plasma. And these are medium-sized particles. They can't be filtered by a traditional filter paper, you know, the filter paper that allows that you put coffee in there, so that way some of the coffee particulates can go through, other parts cannot. But in general, they can't be filtered by those filter paper. They can be separated by semi-permeable membranes, because the semi-permeable membranes they'll allow some proteins to go through, but mostly the proteins will be too big to go through unless you have really big holes on your semi-permeable membrane. And then something weird on this one is the Tyndall effect. Now it turns out that solute particles or colloids are so big compared to the true solution solute particles that if I were to sit there and shoot a beam of concentrated light, or even a laser, the particles are so big that the laser will reflect off and scatter light. True solution particles, such as NaCl, are so small that essentially the focused light or laser will just pass on through. So below we have a nice homogeneous mixture of a true solution particle, such as sugar water, and the light from the from the light passes right through the glass containing the true solution. However, when it hits the glass containing the colloids, and this could be proteins that are floating around in here, it's going to bounce off the proteins, and that's where you see the light beam. The light beam is because it's bouncing off of the proteins in this example and getting scattered. So we call that the Tyndall effect. So that's a positive test to verify that you're dealing with colloids in your solution. So smoke particles from a fire, proteins, oil droplets, those are all examples of colloids. Suspensions, these are very large particles. So these are like sand or dust particles. Muddy water you can consider a suspension. Now it's counterintuitive, but whenever you have a suspension, the large particles are so big that gravity takes over and it pulls it to the bottom. So eventually you'll have a whole bunch of collected suspension on the bottom of the beaker. Again, the name is counterintuitive because it's suspensions where they must be stirred to stay suspended, otherwise they'll fall to the bottom and get deposited on the surface of the bottom of the surface of the glassware. So they settle out easily and must be stirred to stay suspended, and obviously they cannot be filtered at all. There are even larger biomolecular components in your blood called blood platelets, and they're huge. Obviously it cannot be filtered by a standard filter paper, and it won't go through a semi-permeable membrane. And then muddy water, and then types of lotion, what we call emulsions, a type of lotion called emulsions. It rhymes, yay. Those are also examples of suspensions. So know those three terms, and you can just know the face value characteristics of what you see here. That's good enough. Let's go into osmosis and osmotic pressure. So I'm going to go ahead and use a cell membrane in my example. And inside the cell membrane, I'm going to go ahead and put in there a whole bunch of sodium chloride solute particles. And then outside the cell, I'm just going to put a few. Here's my water. Here's a couple of waters that are inside the cell, and then there is a lot of water that's outside the cell. Now, we learned that water loves to surround and hug solute particles and put them in a special formation called a solvent cage, where the partial negative and partial positive on the water molecules help to balance out the charges of solute particles. So, solvent cage. Now, sodium chloride and other solute particles is just like money on the ground. So if you have a 5-year-old and they see some money on the ground, then obviously the 5-year-olds are going to go ahead and surround the money so that they could pick it up. Now let me ask you this. If I had some money right here, and then on the inside of the cell, I had a ton of money. So I'm trying to draw crude dollar bills. It's a numbers game for a 6-year-old. They're going to go to a place that has the most amount of money laying around. So if they had a choice between either going over to the corner over here or going inside the cell and near the money on the inside of the cell, they're probably going to go inside the cell so that way they can get the most amount of money. So again, this is a numbers game. Water molecules do the exact same thing with solute particles. It's like money to a little child where, and maybe I shouldn't say 6, maybe I should say something like 10. Now if I had candy all over the place, that'd be a better analogy. So let's assume they're teenagers. There you go. They like money. So we'll just upgrade these stick figures to teenagers. So that messy statement is supposed to say teenagers. Let me write it again, because, oh, that's not much better. Ironically, this may be the worst spelling of teenagers I've ever written. But you get my point. The teenagers are going to go in the place where there's the most amount of money. Ergo, the water molecules will move into the place that has the most amount of solute particles. So osmosis is when water molecules can pass through a semi-permeable membrane in order to surround solute particles. So if there's a lot more solute particles within the cell, then a lot of water will go ahead and pass through the cell's semi-permeable membrane in order to surround the solute particles and put it in a solvent cage. So osmosis is the passage of solvent, such as water, through a semi-permeable membrane, such as a cell, that separates a dilute and concentrated side. So in this case, inside the cell, the red represents different solute particles. I would consider that a concentrated side. Whereas on the outside, there's not as many solute particles compared to the inside of the cell, so it's a dilute side. So it's the passage of the solvent through a semi-permeable membrane that separates a dilute and concentrated. Now, vice versa, I could have a situation like this where there's not that many solute particles on the inside, but there's a lot on the outside. In which case, you could probably already guess that the water is going to be going the opposite direction. Now, let's get into the terms osmotic pressure. We have two definitions. We have the working definition. It's not a true definition that we like to use in science because it's not measurable. And then we have the textbook definition. This is an ugly definition that's hard to understand, but we like using it because it's measurable. We can take measurements using different types of instruments and perform experiments with it. So let's go through the working definition. Here's my semi-permeable membrane. I'm just arbitrarily going to choose to make the inside the concentrated side. So there's the concentrated side. And then the red dots represent solute particles that are, and this is going to be the dilute side. Water always travels in the direction from dilute to concentrated because it wants to surround the particles in a solvent cage. So as you can probably tell, it's going to push its way in here. Going back to the analogy of teenagers and money, I said that they'd want to move in a position to get the most amount of money. More importantly, are they going to be very kind and respectful to their fellow teenagers, or are they all going to push their way in there in order to get the money? Well, they'd probably push their way in there. Water is the same way. it loves to push its way into a place where there's a high concentration of solute particles. And it literally pushes its way in there in order to surround the solute particles in a solvent cage. So we call this osmotic pressure. And that's the pressure due to the water pushing its way into an environment so that it can surround a high concentration of solute particles. So here's the working definition. Water loves solvating, and it will push its way to a concentrated side in order to accomplish this. So here's the solute particles that I'm circling. I'll circle with a purple pen. That I'm circling with a purple pen right there. And so therefore the water, and I'll draw water on the bottom, that's the dilute side, is going to push its way through the semi-permeable membrane such as a cell membrane and surround the solute particles. Now we need a way of measuring this pressure. So we redefined osmotic pressure with this definition. And let me explain it. So here we have a beaker full of a dilute solution, and you see that there's solute particles in here, and then it's implied that there's water that's floating around. And then we have a test tube in here, and inside the test tube we have a concentrated, because you can see with a deep purple that's the solute particles in concentrated form. There's a lot more in there. And what we did was we put a semi-permeable membrane. It allows water to pass through, but the holes are so small that these solute particles, even though they may be true solution particles, these solute particles cannot fit through the semi-permeable membrane. Only water can. Now, I'm going to draw water in red. As you can guess, water is going to go ahead and push its way through the semi-permeable membrane upward in order to surround all of those lovely solute particles. It applies a pressure when it does this. What happens is the pressure is going to go up. So we're going to be mean. We put a little tiny steel cylinder in here, and we're going to apply a pressure down at the same time. And so as the water applies a pressure up, we are going to apply a pressure down. And the pressure that we apply down, we can actually measure and record. And we have special instruments to help record the amount of pressure, which is pretty cool. So we now need a new definition of osmotic pressure, and this is it. It's the pressure applied as we push down using our instrument to prevent the net flow of solvent, that's the water molecules, through this semi-permeable membrane from solution of low concentration to solution of high concentration. So we put pressure and we measure that pressure just enough so that way it stops the inflow of pressure from the water molecules that want to try to surround the solute particles. So it's the pressure applied to prevent the net flow of solvent. So that's the official textbook definition, allowing us to measure osmotic pressure. So make sure you have this definition down and memorized, or be able to recognize it at least. And then please know that the larger the difference in concentration, the greater the pressure from the water as they become more desperate. To use an analogy, think back to those teenagers. You got a bunch of teenagers, and here I have $1 billion. How likely are these teenagers going to push in order to get the $1 billion versus pushing to get $10? They may be very respectful trying to get that $10 bill. However, if you offered them a $1 billion token, then they're really going to push their way in. Same thing when it comes to magnitude and osmotic pressure. The greater the magnitude, the more concentrated the concentrated side is versus the dilute side is, then the more osmotic pressure from desperate water molecules trying to get in. So larger difference in concentration, greater magnitude of osmotic pressure. So make sure you have that definition down. Let's go ahead and finish this up with a calculation and then some applications. We need a way of measuring the amount of total particles in use of pressure units. So we talked about the difference in concentration. The concentration is the total number of particles that are present. The more particles present, then the more osmotic pressure that's going to be. So we have a way of quantifying it. The greater the osmolarity, or the greater the number of total particles, regardless of whether they're ions or molecules, then the greater the osmotic pressure. So this is how we come up with the calculation. You don't have to apply it to osmotic pressure. You just need to be aware of this unit, osmolarity. And then in future science classes, you may get into it. So this is what I will give you. I'll give you a problem like this. For 2 molarity in ACl, what is the osmolarity? It's pretty easy to do. All you got to do is take the molarity. Oops. Sorry, let me jump back in there. It kicked me out. I love technology. So here's a definition of osmolarity. Let me say it again. To do the calculation, you need to multiply the molarity that I will give you times the number of particles. So for example, sodium chloride that you see right here, I know I'm working backwards, but sodium chloride is broken down into sodium and chloride ions. It's a strong electrolyte, so it completely dissociates. So there's a total of 2 particles. So we say 2 molarity times 2, and that gives you 4 osmol units. So let's do each one of these. We have, what's the osmolarity of each of the following solutions? 2 molarity times, let's see, this would break up into 2 ions. That's a total of 2 particles. So 2 times 2, that's going to be an osmolarity of 4. The next one is calcium chloride. Calcium and chloride break up into 3 particles. Let me just go ahead and write it out. 1 calcium and 3 chlorides. So it's going to be 2 times 3. So it's got a osmolarity of 6. So it's 6 osmol units. Sodium nitrate, having memorized that nitrate stays together in a polyatomic ion, it's going to form a sodium and a nitrate. So a total of 2 particles. So 3 times 2 is 6. So in short, the first one is going to be 4 osmol units. The next one is going to be 6 osmol units. And the last one is going to be 6 osmol units. The trick on these is to make sure you know what ions form, and if you recognize a polyatomic ion, it stays together like nitrate does. So hopefully you have all of those polyatomic ions memorized. Now, the next part, we talked about blood cells, or cells in general, to demonstrate the concept of osmosis and osmotic pressure. So now, here's a scenario where we want to see what effect does osmotic pressure have on a red blood cell. So I'm going to give you 3 scenarios. Let's start off with the isotonic solution. I'm going to go ahead and draw 3 solute particles on the inside of the cell, 3 solute particles on the outside of the cell. Water doesn't care to move in or out of the cell because there's equal number of solute particles on each side. So iso means equal, and then tonic refers to the solute particles. So equal solute particles on the inside and outside of the cell. So there is going to be no effect on the cell. Now let's take another situation. Here is my cell. There's 3 solute particles. We're going to be dealing with a hypertonic solution. So this is the solution surrounding the cell. Hyper means more. So there's more solute particles in the solution than on the inside of the cell. So that's what hypertonic means. So I'm just going to go ahead and draw a whole bunch of solute particles. Now, what's going to happen is water is going to want to go ahead and exit the cell because it's going to be greedy and it's going to want to surround the all those solute particles on the outside of the cell in solvent cages. Consequently, the cell is going to go ahead and crenate or shrink. It looks something like this because all the water evacuated. So this is one of the reasons why if you're dehydrated and you're in the hospital and the nurse wants to put a saline drip into your arm so that way you get fluids through your blood, they have to make sure that the solute particles such as sodium chloride is isotonic. If the solute particles are too concentrated in the solution, making it hypertonic, then it could cause your blood cells to actually shrink and then it could kill you. Crazy. So let's do another situation. Here's hypotonic. So here I'm going to go ahead and have quite a few solute particles on the inside of the cell and then very few on the outside. So hypo means low, and then tonic refers to the solute particles. So there's low solute particles in the surrounding solution of the cell. Consequently, the water is going to go ahead and rush inside the cell in order to surround all the solute particles on the inside of the cell. Now, if you were to receive water through a saline drip into your arm, and it was just mostly water and very little solute particles such as sodium chloride, that could also kill you. Because you have pure water that's being put in you, then all the water could try rushing into all of your cells with the solute particles, and then all that bunching together of water molecules due to osmotic pressure pushing their way in there could cause the cell to burst. So here I'm just going to write the word burst. Also known as cell hemolysis, or the cell's rupture. So please memorize these 3 different solution scenarios and how they might affect your red blood cells, depending on what type of solution you add to the red blood cell, whether it's hypertonic, isotonic, or hypotonic. So this concludes the commentary for the intermolecular forces and solutions, part 2.